Today we're going to be looking at how collisions work, which is one of the most important applications of momentum. To understand how collisions work, we are going to use the law of conservation of momentum to figure out all the math, but there's also some vocabulary that we need to know to be able to describe the different types of collisions we're going to deal with. So what I'm going to do right now is I'm going to do some demos to both show you what the problem solving looks like and what that different vocabulary is. And then after this, we'll go into regular notes where we'll write down the formal definitions, and you'll get a chance to see how all the problem solving works with numbers and diagrams that we'll draw as well. So when we have a collision, which is when we have one cart running into another cart, for example, what we want to be able to figure out is based on how each one of them was moving before the collision and based on what their masses were, what are they going to be doing afterwards? And there's a bunch of different ways that can happen. The first type of collision that we're going to talk about is called an elastic collision. So we think of elastic as being something sort of stretchy or bouncy, and that's what happens in an elastic collision. They bounce off of each other. And the way they bounce off of each other causes they bounce off each other perfectly, so they don't wind up losing any of their kinetic energy. No kinetic energy gets converted into heat. And so to demonstrate that, I have some magnets built into the end of each one of these carts, so that when they get near each other, they'll be able to push on each other without actually hitting each other. Because if they actually were to clonk into each other, that sound that you're hearing requires some energy, which would have come from kinetic energy, and also we'd have some heat being generated as the plastic molecules deformed against each other. So by using the magnets, we can have them just bounce off of each other and not lose any of their kinetic energy. And so a simple example we could look at is, well, what happens if this one starts at rest and this one is moving towards it? What's going to happen when they run into each other? Well, the law of conservation of momentum, which is what governs our collisions, the total momentum before and the total momentum afterwards has to be the same. So this one, if it is moving at maybe 4 meters per second in this direction, and it has a mass of half a kilogram, its total momentum is going to be positive 2 then. Positive 4 meters per second times half a kilogram, 4 times 1/2 is positive 2. And if this one's not moving at all, its momentum is going to be 0. And so the total momentum is going to be positive 2 from this one and 0. And so the total momentum is positive 2 before. Afterwards, the total momentum has to be positive 2. Well, let's see what that looks like. So this one's going to run into the other one. And we can see what happened was this one wound up stopping, and this one took off at the exact same speed, still going in the same direction, so the exact same velocity. And that should make sense because they have the same mass. And so when this one stopped moving, its momentum was 0. But we know the total momentum had to be positive 2. And so that means that this one had to have the entire positive 2 momentum. And since its mass is only half a kilogram, it would have to be moving at 4 meters per second, just like this one was at the beginning. And so in an elastic collision, when their masses are the same at least, they just basically trade velocities. Now we can change that up by altering the mass of one of them. So if we make the initial cart more massive, now something a little different is going to happen. When they hit each other, now they're both moving and they're moving at different speeds, but if we were to calculate what the total momentum of both of the carts before was and both of the carts afterwards, we would still see that the total momentum was conserved. And we'll practice doing that when we get to our problem solving. The next type of collision is called an inelastic collision. Oh, I'm sorry, there's one other thing I wanted to show you with elastic collisions. So there's going to be a couple demos that I'll show you with each style of collision. One is that one where this one starts at rest and this one is coming in. The other one I want to show you is what happens if they are both moving towards each other. And if they're moving at the same speed and they have the same mass, that'll mean they have the same amount of momentum, but it'll be in opposite directions. So if this one's momentum is positive 2, and this one is going the other way, it'll have a momentum of negative 2, which means our total momentum at the beginning is going to be 0. And after the collision, if momentum is going to be conserved, the total momentum still has to be 0. And so we should see after they collide with each other, that they wind up going in opposite directions at the same speed, which means that they'll still have momentum of 0 because they basically just traded momentums in this case. This one went from having a momentum of +2 to -2. This one went from having a momentum of -2 to +2. So at the beginnings, the momentums were +2 and -2, which is 0. At the end, the momentums were -2 and +2, so we still had a total of 0. And in this case, because no kinetic energy was lost, they wound up going at the same speed. It looks a little bit different again if we change their masses. Now, if they're moving at the same speed, they're going to behave differently when they hit each other. But again, we can use our problem solving that we'll do once we get to the regular notes to figure out exactly how to solve that as well. Okay, the next type of collision is called an inelastic collision. In an inelastic collision, they still bounce off of each other, but the collision is a little messier, and some of our kinetic energy winds up getting converted into heat. It's because the parts of the carts actually hit each other, and there's some deformation and some random motion that happens in like the plastic molecules that causes us to have some of our energy that was useful, kinetic energy, get converted into heat. And so I'll just flip this cart around so it doesn't have a magnet. And so now when they hit each other, there'll be sort of a thunking noise so we know they're actually hitting each other. And we'll repeat a couple of the demos that we did and see that it looks a little bit different because they are different collision types, but we're still going to have momentum be conserved. So the first demo I did, this one starts at rest, its momentum is 0. This one comes in at 4 meters per second, so its momentum is +2. So momentum of +2 and 0, total momentum of +2. Let's see what this looks like in an inelastic collision. All right, that's a little different than our elastic collision. In the elastic collision, this one just stopped. In the inelastic collision, it kept going forward a little bit. Which meant that it didn't lose all of its momentum. It went from having a momentum of +2 to maybe only having a momentum of +0.5 or something. Since the total momentum at the end still had to be +2 though, that would mean if this one ended with a momentum of 0.5, this one must have picked up a momentum of 1.5. And so it would have to be moving significantly faster than it was at the beginning, because it wasn't moving at all. But it's not going to be moving as fast as this one was to start, because if this one started off with 2, and this one only ends with 1.5, because this still has 1/2 a kilogram meter per second of momentum, this one doesn't have as much momentum at the end as this one did to begin with. And since they have the same mass, it won't be going as fast. And so I'll do that one more time so you can see that happening. They have the same mass, and we'll see after the collision, this one is still going forward a little bit, and this one is going forward pretty quick, but not as quickly as this one was at the beginning. And if we do the math, we'll still see that our total momentum is conserved. It's just distributed differently. We went from a momentum of +2 and 0 for a total of +2 to have it being it's somehow split, maybe 1/2 and 1.5, as opposed to 0 and 2, like in the elastic collision. The other demo I want to do again is the one where they're both going at the same speed and they hit each other. In this case, our total momentum was 0, because this one has a momentum of +2 and -2. In this case, we'll see when they hit each other and bounce off. Once again, they go at the same speeds as each other away, so that they still have a total momentum of 0, but they're not moving as fast as they were at the beginning. So maybe they slow down a little bit. This one goes from having a momentum of +2 to maybe a momentum of -1.5. This one goes from having a momentum of -2 to +1.5. So at the beginning, momentums are +2 and -2 for a total of 0. After the collision, momentums are -1.5 and +1.5, so we still have a total momentum of 0. But they're not going as fast as they were in the first place because some kinetic energy gets lost. Remember, that's our definition of an inelastic collision. The last true collision is called a perfectly inelastic collision, or a completely inelastic collision. And that's where they actually stick together and become a single object. This involves a tremendous loss of kinetic energy because they have to somehow deform enough to actually get stuck together. And so I can demonstrate this with some Velcro that I have on the ends. And so when they stick to each other, now they'll become a single cart. But even though they become one object, we still have to have momentum be conserved. And so we'll repeat our two demos again. Initial momentum here is 0. This one's going to be coming in with a momentum of positive 2. At the end, their total momentum has to be positive 2. Well, that looks different. Now, since they're moving together, we've basically gone from one moving object, one small moving object, to one larger moving object. And the total momentum, though, still has to be positive 2. Since at the beginning, though, only had half as much mass, remember this was half a kilogram, coming in at 4 meters per second, the total momentum is 2. When we stick two half-kilogram carts together, their total mass is going to be 1 kilogram. And so in order to have that total momentum of positive 2, if their mass is 1 kilogram, they've got to be moving at 2 meters per second. And so we go from moving at 4 meters per second and 0 to both of them moving together at 2 meters per second. And so we can see they slow down. This one winds up, because we're basically doubling the mass, going at half the speed. But we still have momentum be conserved. The other demo that we did for the other two that I want to repeat here is where they're moving towards each other. Again, this is where we start off with a total momentum of 0, because we have a momentum of positive 2 and negative 2. And at the end, their momentum has to be 0. So some of you might be able to imagine. So we can see they wind up stopping. Because our total momentum went from positive 2 and negative 2, so a total momentum of 0, to at the end, they have to have a momentum of 0, but now they're stuck together. And so the only velocity that they can have if they're stuck together to have a total momentum of 0 is 0. And so we wind up still having our momentum be conserved, but it looks different than it did in the other two conditions. The last situation is called an explosion, and we treat it like a collision because mathematically it still follows the same rules, but it's really the opposite of a collision. In an explosion, we have one object that becomes two. And so we can demonstrate that with, I have this little spring-loaded plunger here that I can use to have them push away from each other. So we're going to start off with some energy stored inside of here. And then after the explosion, we're actually going to have a gain of kinetic energy. So we'll have these starting off together as a single object. Total momentum is 0 right now because our velocity is 0. And then if I hit the button, the total momentum still has to be 0. If they have the same mass, that's going to wind up looking like this. So we can see they wind up going in opposite directions at the same speed. They need to have opposite velocities. So if this one flies off at 4 meters per second in the positive direction, this one would have to be negative 4 meters per second so that their total momentum would be 0. A momentum of positive 2 and negative 2 for a total of 0. If we change up the masses, if I now increase the mass of this one, so this cart is still just half a kilogram, but this is now 1 full kilogram, they're going to behave a little differently. The total momentum, if they start off at rest here, still has to be 0. But now, since they have different masses, they're going to have different speeds so that their total momentum can still be 0. We go ahead and hit the button now. We see that this one wound up flying off significantly faster than this one. Because if this one went off at 4 meters per second, for example, 4 meters per second times half a kilogram would give us a momentum of positive 2. Well, that means this one's got to have a momentum of negative 2, so the total momentum can be 0. But if its mass is a full kilogram, it's only going to be it only has to be going at negative 2 meters per second. And so this one goes forward at 4, this one goes backwards at 2, and so this one winds up going faster. Because their momentums have to be opposite, so the one with less mass has to have more velocity. So over the next couple of videos, we'll go over the just the definitions of all the collision types, and then we'll start looking at how to set up our problem solving, how to draw the diagrams that we need, how to do all the math.